Physicists have just announced the detection of the most massive black hole collision ever seen, producing an object around 50% more massive than the previous record holder. What does this mean? Let's press play and find out. This is our channel. But then I read on and learned about an event that happened 2 billion light years away, and I felt much better. When I saw the title of this news release, I thought, oh great, not another black hole that eats everything in its path, including my homework. It's the event, called GW231123. It was detected on November 23, 2023 by the LIGO Virgo KAGRA network, but even that would beat the current record. In any case, let's take a closer look at some of the highlights. That's the global network of detectors searching for gravitational waves. A rapidly spinning black hole is closer to the theoretical limit of what's physically possible, and astronomers want to understand how this came to be. In this case, the signal was less than 0.1 seconds long, yet it was clearly visible across LIGO's frequency spectrum, which starts around 60 Hz. The previous record holder, GW190521, produced a 142 m black hole from two progenitors of about 85 and 65 m. Since their theoretical prediction in the 1970s, IMBHs have remained elusive, with only a handful of candidates ever identified. By analyzing the properties of the merging black holes, astronomers can reconstruct the conditions under which they formed. Gravitational waves, ripples in the fabric of space-time caused by the acceleration of massive objects, offer a unique window into the most violent and energetic events in the cosmos. It underscores the need for next-generation detectors such as the proposed Cosmic Explorer and Einstein telescope, which aim to achieve even greater sensitivity. By pushing the boundaries of gravitational wave research, scientists hope to unravel more mysteries of the cosmos and deepen our understanding of the fundamental laws of nature. LIGO and its international partners have been at the forefront of this research, operating highly sensitive interferometers to detect these elusive waves. The ability to observe such massive black hole mergers not only expands our understanding of the universe, but also demonstrates the remarkable precision and sensitivity of gravitational wave detectors. The fact that both progenitors were in the 100 to 140 m range suggests that they underwent multiple mergers, gradually building up their mass through repeated collisions. This challenges previous theories that predicted a gap in black hole masses at these high values. This is partly because they're hard to spot, as they lack the telltale bright lights of quasars, which are powered by materials swirling around supermassive black holes. Instead, IMBHs are thought to reside in the murky depths of space, merging with other black holes or lurking at the cores of smaller galaxies. The confirmation of the 225 m black hole as an IMBH marks a significant step forward in our quest to understand these mysterious objects. And check out our other videos. Thanks for watching. See you next time. This event was also notable because it already pushed into the intermediate mass range. However, GW231123 upgrades this result with even more massive and faster spinning progenitors and a more extreme final mass, driving the total mass to the limit of what's theoretically possible. Signals from lower mass systems tend to be longer and higher in frequency, making them harder to detect. In this case, the high masses involved meant that the signal was short, but easy to see. Possibilities include rapid rotation from the collapse of an already rapidly rotating star, or previous mergers in a dense environment. For example, previous mergers can cause significant angular momentum transfer and increase the spin rate of the black holes involved. An intermediate mass black hole, or IMBH, is a rare and elusive class of object that falls between stellar mass and supermassive black holes. Currently, astronomers have no convincing evidence for black holes more massive than about 60 m. That's because in the 60 to 130 m range, standard stellar collapse should fail. Above 60 m, the core of a massive star collapses at the end of its life, leaving behind a neutron star. But if the star is too massive, its core will collapse straight to a black hole. However, in the process, it blows off a substantial amount of mass, which prevents the black hole from getting too heavy. This is known as a pair instability supernova. It turns out that pair instability gets stronger the more massive the star is, blowing away almost everything and leaving behind a relatively small black hole. The problem is that this process should get more efficient as the star becomes more massive, preventing black holes above 130 m from existing. These forbidden masses pose a challenge to our understanding of black hole formation. The existence of 100 to 140 M black holes suggests that they likely did not form via direct star collapse, but instead they likely formed via hierarchical mergers. In other words, they built up their mass gradually by merging with other black holes. Mergers can occur when a star cluster is very dense, like in the core of a galaxy, or in the dense outskirts of a globular cluster. Such dense environments bring a lot of black holes close enough together that they can merge. And if they merge multiple times, the result can be a black hole several hundred solar masses. While we expect IMBHs to exist, they remain somewhat theoretical. There have been some candidate observations, but none has been confirmed. The existence of the 225 solar mass black hole strongly suggests that IMBHs do exist. And that's why this discovery made headlines all over the world. The event was produced by the merger of two black holes with initial masses of about 100 and 140 M, where M is the mass of the Sun. They merged to form a final black hole with a mass of approximately 225 M. This final black hole is now the most massive ever seen, surpassing the previous record holder, GW190521, which produced a 142 M black hole. In any case, let's get to the key facts. Now, these numbers are very rough. The uncertainties are quite large. It's possible the final black hole could be as small as 200 solar masses. First, the final object is only the second known intermediate mass black hole. Second, the existence of the 100 to 140 M black holes suggests that there are more of these objects out there than we think. Third, the progenitors were spinning at a large fraction of the maximum limit allowed by general relativity. This makes modeling more difficult. Finally, the signal itself is noteworthy. Gravitational wave signals are extremely short when the masses are high. It's worth noting that this isn't the first time physicists have seen a massive black hole collision. What makes this new discovery particularly exciting is that it sheds light on the enigmatic world of intermediate mass black holes. Moreover, the study of GW231123 provides crucial insights into the formation and evolution of black holes. The detection of GW231123 also highlights the extraordinary capabilities of gravitational wave astronomy. Furthermore, the detection of this massive black hole merger has significant implications for the future of gravitational wave astronomy. As always, I hope you enjoyed this video. If you did, don't forget to subscribe.